So in this video, I want to define what an infinite Cartesian product is. Recall that a Cartesian product of sets, say we have sets A1, A2, all the way to AN, and we have a finite number of these sets, specifically n of these sets. We define the Cartesian product of this, which is in red, A1 cross A2, or times A2, cross all the way cross AN, we define this as the ordered n-tuples. That's a good vocab word. N-tuples, A1, A2, all the way to AN, such that for all j between 1 and n, so all j in the set 1 to n, a sub j is chosen from the set AJ, right? So these are all these collections of n terms where each term is chosen from their respective set in the product, okay? So a natural question would be, how could we extend this to the infinite case? If I were given not a finite number of these sets, but let's say we have countably infinite number of these sets, A1, A2, and we just keep going on to infinity. How could we define this notion of an infinite Cartesian product? And kind of one guess would be, okay, we have an n-tuple here. Is there something like an infinite tuple where we have this infinite list of terms where each term is taken from, A1's the first, A2's the second. We just keep going for arbitrarily long. Okay, that I think that's not a bad idea, but also an infinite tuple is a little bit, I think that's getting a little bit kind of that's pushing it a little bit. That's not super, I don't think that's rigorous enough. That's not satisfying enough. Is there a structure in math that we've learned that kind of takes this role of an n-tuple? And there is, it's a sequence, right? And sequences do a really good job, not just, being able to manipulate sequences, but they do a really good job of kind of serving as an infinite tuple of elements, A1, A2, and so on. So we can define a Cartesian product of an infinite number of sets. So an infinite Cartesian product actually in terms of sequences, not in terms of n-tuples. And this, I think, works a lot better. We'll define the infinite Cartesian product as the set, the collection of all sequences now, a sub n from 1 to infinity, n is 1 to infinity, such that, very similar to here, for all natural numbers j, so now instead of dealing from 1 to n, we're dealing with all natural numbers 1 to infinity, a sub j is chosen from your jth set in your Cartesian product. I really want to emphasize, I think this is a really good definition. It, seems very natural. Sequences serve as our kind of infinite tuples. The only catch is this is really different from the idea of our normal Cartesian product, which is defined as, kind of ordered finite lists of elements. This is now defined in terms of sequences, which are ultimately functions. So in this case, a sub n would be a function from the natural numbers n. Hey, that corresponds with the nth term in your sequence. And then the output is some element within a sub j. So a sub n in whole maps from natural numbers onto the union, or into the union from 1 to infinity of your a sub j's. So this is we're defining this in terms of a function. Okay, that's fine. I think that's a satisfying definition. I think defining it this way has some really interesting consequences. And to also distinguish, to really emphasize, this is defined in terms of sequences, instead of writing A1 cross A2 cross and so on with, 3 dots representing, yeah, this goes on infinitely, we write it in big pi notation. This is product notation, which you can compare to sigma notation if you haven't seen it before. This is the product, we index it from 1, and is 1 to infinity, of a sub n. This is notation, this is the notation for an infinite Cartesian product, and it's defined as all sequences such that the jth term in the sequence is chosen from the jth element in your infinite Cartesian product. I said there's some interesting consequences of defining it this way. I'll mention one now, as well as an example of a Cartesian product, right? We'll let, I don't know, B be the set 0, 1. So kind of just this binary set, 0 and 1. It's a very simple set, but just with this simple set, what happens if I take the Cartesian product n is 1 to infinity of B? Well, this is defined to be the sequences a sub n from 1 to infinity, such that the jth term here, a sub j, is chosen in B. Well, B is 0, 1, so this is a sub j is either 0 or either 1, and so this Cartesian product is defined as the collection of binary sequences. This is the collection of sequences where either a term is 0 or a term is 1. I think that's kind of really interesting. What's also interesting is you might know or you might not know, I won't show it here, that the cardinality of this set, the number of binary sequences, is actually uncountable. So this is actually uncountable. So that even though B is a finite set, it's a very small set, and we're taking a countable Cartesian product of it, we could end up with something far larger, an uncountably infinite set. And last thing I'll throw in, again, I won't spend too much time talking about this, but infinite Cartesian products are actually used to define the axiom of choice, arguably the most important axiom and widely accepted axiom of, how do you spell choice? Okay, choice. This is often the most accepted axiom in all of math, in almost any field of math, and it's defined, the formal statement of it is defined in terms of infinite Cartesian products. So these things are really interesting and are really useful. I want to talk about them a little bit more next time.